Hello, and welcome to our next set of statistics notes. We are on Chapter 11, and we have a couple different tests we're going to hit in Chapter 11. This first section will hit the goodness of fit test. We'll have a couple of other tests we're going to hit. That's really what we're going to finish off with these three different tests in the three different sections in Chapter 11. The first test we're going to do is the goodness of fit test, but before we get to do the goodness of fit test, we need to introduce the chi-squared distribution. So we've had the standard normal curve, we've had the t-distribution, we've had the distribution for the r values for the linear correlation coefficient. So we have all these different curves. So you do have one more for this section, and it's a chi-square distribution. It's a little different than our distributions because it is one where it always starts at 0 and it's always going to have positive values. So we use this specifically for just this goodness of fit test. So this is, I think actually 11.2 might use this as well, if I remember correctly. But that's about it. There's not a whole lot of stuff we use chi-squared score for. Just like the t-distribution, this does depend on degrees of freedom. So it's going to be different degrees of freedom are going to cause different shapes for this. So let's look at some of the properties of this. First off, the total area on these is always going to be 1 equal to 1, meaning that 100% of the values lie underneath the curve. So the total area, the percent or probability is 100%. So whenever you draw a curve, underneath of it's going to have all the values. The chi-squared curve always starts at 0, so you can't get negatives for this. You only can get 0 or up. And then it goes on forever in the right direction. Never quite touches, it just kind of gets closer and closer, but never quite touches. It's always possible to get value up high, but most of the time you won't because those are going to be very, very rare. So never touching the horizontal axis. It approaches it the whole time and extends indefinitely to the right. It is obviously right skewed because it stops at 0 and then spreads to the right forever. So it's always going to have a wider right side than it does a left side. So it's going to be right skewed. And then degrees of freedom, as that becomes larger, the chi-squared curve becomes more like the normal curve. So it becomes looks increasingly like the normal curve. So the bigger the degree of freedom, the more this is going to look like that normal bell curve, that standard normal distribution. So just like finding percentages, probabilities for variables when we use the t-distributions, we can do this for the chi-squared distribution. So we'll do that here just to show you how it works. So we have a chi-squared distribution with 17 degrees of freedom, and we want an area 0.1 to the right. So we're looking for a chi-squared value. So we're looking for chi is like a fancy x, chi-squared value. It's going to have area 0.1 to the right. So if I look at the distribution, it's going to be something like this, where the degrees of freedom is 17. And so we're going to mark off an area, and this area is going to be 0.10, and we're looking for the chi-squared value that would mark off that area. To do this, we'll use a chart. There is a chart for this. This chart is available in my last lab. So since our degrees of freedom are 17, we're going to look at there because that's our degrees of freedom 17. And we wanted 0.1 to the right, because these are all areas to the right at the top, right? So you see area to the right at the top. Have really big numbers, really small numbers. They kind of skip the ones in the middle because we won't really use those. Most of that we would use the ones over here that are really small. So 0.1 with 17, I come down here, 17 looks like it's right there. So that's 0.1 to the right, degrees of freedom of 17. So the answer to this chi-squared score we need would be 24.769. So chi-squared is 24.769. That is the chi-squared score that has an area of 10% or 0.1 to the right. You're not going to really need this a whole lot for this section, maybe if you answer a question like this, but we'll see how most of the time if you use technology, we don't need to do that by hand. So we'll use it a couple times just for practice. Okay, now what is the goodness of fit test? Now that we talked about chi-squared, let's talk about the chi-squared goodness of fit test. So this is for when we want to perform a hypothesis test about a distribution of either a qualitative or discrete quantitative variable. So something that's only got so many options, things that could be qualities, that could be labels. Only has finite possibilities. Below would be an example. So this one's looking at types of violent crime. So these are things you can label. They're qualitative data. And they only have so many labels, right? There's only so many different sets that can be included in. And what we're going to test basically is we're going to look at, usually look at like previous results, like what study showed years in the past. So like maybe before an elected official came into office, they did a study and figured out what percentages of the different violent crimes there were. And then after they came into office and enacted some new policies, we'll use the chi-square goodness of fit test to see if the data still matches what it was before. If, excuse me, sorry. We're going to look and see if maybe they change the percentages because of the policies they employed. So a chi-square goodness fit test is to look if the data still reflects what it was in the past. It's going to kind of observe if there's changes, if it still fits. So if it fits with your expectations. Usually, of course, expectations are developed in the past. That's usually how it works. So you'll have the percentages that people have gotten from like a study in the past. You'll have your observed what you got report. So like they just looked it up last year and this is what they got. And then they'll take the how many they studied. So they studied like 500, and they'll look at the percentage they were expecting, and they'll get the expected frequencies. These are the numbers they were expecting. So I can compare those and say, well, they got 3, but they were expecting around 6 of the first one. They got 36, but they were expecting only 34. So that way they can compare and see which ones have increased and which ones have decreased. Like the aggregate result here, they were expecting 312, but they only got 291. So that's what we're going to be comparing with the chi-square goodness of fit test. We're going to look at the rates we expected versus the rates we got. And again, we get the expected rates based on the percentages we've already known about, from reports we've already done. Now, there's going to be 2 main ways to deal with the expected frequencies, the values we got here. One is there'll be times where you just expect everything to be equal across the board. So you just think things should be spread out evenly. And so that's when you do this calculation. You'll take n, which is your sample size. In this case, it was like 500. And you should divide by k, where k is the number of categories. So k is just the number of categories. And the sample size, k is the number of categories. So like in this case, we had 4 categories. We'd just take 500 divided by 4, and that's how much we'd expect per category. But we don't really expect murder and robbery and assault and rape, all that to be equally spread out. That's not really going to happen. So in this case, we'd actually use the not equal, and that's what we did up here. To do not equal, we take the sample size n and multiply it by the relative frequency for the category. So like murder is, what is that, 1.2%. So there's 500 times 1.2%, and that's how they got these 6 potential murders. So for example here, murder gave us the 6, because if you do 0.012 times 500, that's how you get that 6. So they're doing the sample size n times the percentage for murder, which is that percentage. These would be the p's here. This is your n, and that's how they got the expected frequency. This is what they expect to happen. It's not what actually happened. That's we only had 3, which is great. The murder was down, but that's what they were expecting based on past results. Okay, once you have those observed, the frequencies got from collecting data, the expected frequencies, what we expected to happen, then you can calculate the chi-square subtotals, which we'll use to get the chi-squared score and do our test. So to do these, we subtract the values and then square them and then divide by the expected values. So we're going to take the observed values minus the expected values, square those results, and then divide them by the expected value. The sum of these chi-squared subtotals is the statistically used to do a goodness of fit test. So the chi-squared value is going to be the sum of the observed values minus the expected values squared divided by the expected values. This does have a degree of freedom, which is going to be 1 less than the number of possible values. So the degree of freedom for this is going to be 1 less than k. So it's going to be k minus 1. So the number of categories you have minus 1, that's going to be your degrees of freedom for these problems. Okay, how do we do this test? Okay, so here's the rundown. The procedure for doing a chi-square goodness of fit test. Below we lay out the method. Because we only reject the null if the test statistic is too large, this is always a right-tailed test. So the important thing to note, this is always a right-tailed test. We're never going to have a less than or a not equal to. It's always going to be a greater than or a right-tailed test. Okay, the null hypothesis is that the frequency counts agree with your claim distribution or with your expectations. So the numbers still match what they were before. Nothing's changed. The alternative is that they do not agree, and that's going to be basically saying that the frequency we just calculated when we collected the sample doesn't match what we expected. So then it does not agree with the claim distribution. So, you know, stayed the same, changed. So the alternative is going to be proving that, that things have changed. It's different from what we expected. Okay, when you're doing this, you do have to, of course, have some requirements like we've seen a lot of. Randomly selected data is a requirement. The expected frequency must be at least 5 for every category. So if we look at the last one, we have the expected frequencies here. We look at these and say 6, 34, 147 through 12. Those are all big enough. But if you did this and ended up with one of these being less than 5, it means your sample size was too small. And you have to go back and try it with a bigger sample size. So expected frequency is at least 5. That's something to be careful about for every category. Sample data is frequency data for different categories. So the sample data is going to be the actual counts for each category. So that's what your sample data is here. Right here, your sample, you have the counts for each category. That's what you need when you do a chi-square goodness of fit test. This is our test statistic, right? That's the chi-squared value you use for your test statistic. There are 2 approaches. We are not going to really use the critical value approach because the p-value method is just easier. We can use technology for it. So we're really going to work at the p-value method. We'll get the test statistic, we'll calculate the p-value, and as always, if the p-value is less than the significance level, we reject the null. And you'll use this to use technology usually. I'm going to show you once without, but most of the time I use technology. I'll show you both on this one example here, just so you can see the difference, and then you'll probably see why you want to use technology for this. Okay, so here we go. Let's do our example. A distribution and observed frequencies from a sample are provided. So the distribution, this is going to be your claimed distribution. These are the previous results, basically. So these are the percentages. These are always going to be percentages. They should add up to 100% because it's a whole distribution of all the different possibilities. That's what we had in the past. Now this is percentages, right? These are percentages. They're not the frequencies, because frequencies, remember, are counts. So these would be counts. Frequencies are counts. This is the percentages. So we're going to use these to figure out our expected frequencies. We're not there yet. Observed frequencies, these are the results for your sample data. So they took their sample data and they got this. Okay, so a couple things. First off, to find the expected frequencies, we're going to take n times p, and these values are the p's, right? These are the percentages we're going to use. The observed frequencies, you can write those down. So I'm just going to put down the 14, 18, 22, 42. We don't know the categories, but we don't need to. First thing we do need to know the sample size, though. So what's the total sample size? So let's just add those up and figure out how many we have here. So we've got 14 plus 18 plus 22 plus 42. Looks like we have, did I type that right? 14, 18, 22, 42. Yep, 96 in our sample group, right? So we have 96, so our sample size is 96. So to find these expected frequencies, we're going to take that 96 times each one of these percentages. 96 times that 0.0625. So that first one should be 6. 96 times 0.1875. That should be 18. It actually was 18, so that's pretty close to what they were expecting. Next one, I'm going to do 96 times 0.3125. That should give me 30. And then the next one, I have 96 times 0.4375. So we got 42 for that one. Okay, so these are the frequencies they were expecting. Based on the percentages, based on previous data, these were the numbers they were expecting. These are the numbers they actually got. This is the data they collected. So we're looking at the difference between these and seeing if there's enough of a difference, we can say the frequencies are different enough from what they got. Now, yes, they are different, but there has to be enough of a change, because if they're too close together, if the results they got here are too close to what we started with, or what we were expecting, we're too close to our sample result, if these numbers are too close together, then we're going to say that's not enough of a difference. We can't say stuff has really changed. But if these are different enough, we can. So that's what the test is testing. First thing we do is in the test, we subtract observed and expected frequency. I'm going to take my observed and subtract my expected. So 14 minus 6 is 8. 18 minus 18 is 0, so that one's not much of a change. 22 minus 30 is negative 8. 42 minus 42 is 0. Then we're going to take each one of those and square them. So 8 squared is 64, 0 squared is 0, negative 8 squared is still 64, and 0 squared is 0. Then we're going to take each one of those and divide them by the expected value. So we're going to divide them by the e. So we take 64 divided by 6. So that gives me 10.7, something around that. Of course, 0 divided by anything is still 0. 64 divided by 30, so 64 divided by 30 is 2.1. So 2.1. And then 0 divided by anything is still 0. Okay, so these subtotals, we're going to take those and we're going to add them all up. And that gives us our chi-squared score. So if I add those up, I get 12.8 is my chi-squared score. That's my test statistic for this. So we'll use the test statistic to get our p-value. So from the chart on this case, because we're doing it by hand right now, we're going to go ahead and get the p-value. First off, before I can look at the chart and get a p-value, I do need to think about the degrees of freedom. Remember, the degrees of freedom is the number of categories, which in this case is 4, right? There's 4 categories, minus 1. So the degrees of freedom is 3. Minus 1 equals 3. So that's why we use 3 for the degrees of freedom. So 3 for the degrees of freedom, and then we're going to look at 12.8. Now we're kind of going backwards here, because we're actually, the 12.8 is already our chi-squared score. So we want to go back and figure out what the area is, because the p-value is a probability is an area. So at 3, you can see 12.8, it's not exactly, but it's pretty close to this number. 12.838 is pretty close. So we can use 0.005, because that's pretty close. So the p-value for this is 0.005. Now, because they want us to do this as a 5% significance level, that's what we'd be comparing our p-value with. So if we look at that versus the 0.05, which is our alpha, we'll see, of course, that 0.005 is much smaller than 0.05. And so we do have a small enough p-value. Remember that when the p-value is small enough, you reject the null. And if you reject the null with a goodness of fit test, remember that means that the new data, the sample we just brought in, does not match the claimed distribution, this existing distribution. So things have changed significantly. You can see how those two really just changed so much that now you can say the distribution is different. So the observed data, the observed frequency counts do not agree with claimed distribution. So the sample, so I should say frequency counts don't agree with claimed distribution. Okay, that was doing it by hand, which I picked a small set of data, so it wasn't too bad. If you have more categories, especially if they have more of them that are different, so not as many zeros, it can get kind of time consuming. So it is nice to be able to do this in a calculator. The one problem is not all calculators have the technique you use for this. So to do this on your calculator, if you have the nice up-to-date T84 Plus, under your stats and tests towards the bottom, you should have a chi-squared goodness of fit test. So we use the chi-squared goodness of fit test. And to do this one, you're going to have two lists. You're going to have your observed list and your expected list. Oops. I pressed a button I didn't want to. Chi-squared goodness of fit test. So your observed list 1 and your expected list 2. Now, when you put this in, you're not putting in the original data they gave you. If you put these numbers in, you're going to be in trouble. You are going to use this for list 1, because this is observed frequencies. But for list 2, you're going to actually use this. This is your list 2, because they want frequencies, not percentages. So this is something you have to be really careful with when you do this. Don't type in the percentages, type in the frequencies. So you still have to find these frequencies either way. So this step has to be done either way. You have to look at the number of sample, how many was sampled, and if it's percentages like this, you multiply that sample size times each percent, and those are the values you enter in. So that's what you want there. Degrees of freedom, you do have to tell it the degrees of freedom for this. So here you'd have to tell it the degrees of freedom is 3, because that's 4 minus 1. So degrees of freedom is 3. To give it all that information, which is kind of a pain, and hit calculate. and then it should work for you. So we have, oh, you know what I did? I never actually entered my data. Let's do that first. I still have my data from last of the notes. Helps to put that in first. Okay, so the first one, observed values, was 14, 18, 22, 42. Next one, the expected values, we got 6, 18, 30, 42. Okay, so then now I got the data put in there. Now I can go ahead, stats, tests, do that chi-squared goodness of fit test, and now it should work out for me. So from that I got the chi-squared score, which is 12.8. So we did good, we got it right. The chi-squared is 12.8. And then the p-value, which is 0.005. So that was, one if you want to round specifically, but I think I'm okay with saying p-value. It's 0.005. That's close enough for me. And they do put the degrees of freedom, but you gave that, so you don't really, it's not anything new. So that's what we needed. So yeah, we have the chi-squared and the p-value, and then that's what we use to do our test. So, again, we would compare this with a significance level and say this is less than 0.05. Reject. Now, I have a note here about people with an old TI-3 calculator, because the old TI-3 calculator, though it's done pretty much everything else we've done this semester, doesn't have the chi-squared goodness of fit test. Now you're not out of luck, because if you do have a TI-3 calculator, there's actually a way to put in your own chi-squared goodness of fit test. So you can program these calculators. You can program the goodness of fit test. And if you want that program, I actually have it. One of the other teachers I work with, who's really cool, actually wrote his own program for these TI-3 calculators. So just email me to get instructions, and I'll send you his instructions he wrote out on how to make your own chi-squared goodness of fit test. And it's pretty cool. It works really well. In fact, I think it actually finds the degrees of freedom for you, so actually pretty nice. So if you don't have a chi-squared goodness fit test already on your calculator, you have an older calculator like Baby 3 and you want to get this in, then just send me an email and I'll send you the instructions and you can put it in your calculator. Okay, one more example, just to finish it off. We'll do one more example and then we'll be done with this section. So here we go, we have another problem. A group of 1,000 students were asked which is their favorite month. Consider the claim that the month of the year selected with uniform distribution. So here they're saying that we expect each month to be picked equally as often. All the days have the same chance of being selected. All the months, I should say. The table below shows the preference of the students. Test this claim at 5% level. So we're going to test this at the 5% level. Okay. So, to do this test, first off, notice that the expected frequencies for this one are going to actually be using this n over k formula now. Because instead of doing n times p, where we multiply by the percentages, they didn't give us percentages. They just said uniform distribution, which means that we expect each month to have the same number of results. So we could take the 1,000 students that we have and say if they each pick the months equally, often, we can just divide by the 12 different months, and that will give us our expected results. So if I divide that out, 1,000 divided by 12, I get 83.3 repeating. So 83.3, that's going to be our value for our second list. So that's our expected values. This first one is going to be our observed list. So this would be list 1. This would be our list 2. So now I do the chi-squared goodness of fit test. That's the data we'll enter. One thing we do have to know, we do need that degree of freedom. Since this one there are 12 different months, that's what we're dividing by, k is 12, then the degree of freedom is going to be 11, because 12 minus 1 gives me that 11. Okay, so let's put that in here. So do our test. We're going to do stats, tests, scroll down to chi-squared goodness of fit test. Well, I have to put the information in first. I'm trying to do it again without putting the data in. Okay, let's type the data in. The first one, it's just going to be 69 each time. 61, 68, 65, 77, 72, 73, 27, 6, 68, 1, 74. Well, it should be 12 values. You can actually look at this and it shows list one option 12 or entry 12. So we got 12 values. This one's just going to be the 83.3 each time. So I should put that in. I think I have to put it in 12 times. There's probably a faster way to do this, but I don't remember the other way. So I'm just going to put it in there 12 times. Make sure you type it right though. Okay, it doesn't take too long. So that works because this is what we would expect if everybody was equal, right? So that's what we're saying. If all the months were equal, then that would be what we expect. Stat tests. Go down to the chi-squared goodness of fit test. List 1 is the entries up here we have. List 2 is going to be 83.3 for all the entries. Degrees of freedom this time is 11. There's 11 or 12 months minus 1. And that should give us our values. So from this, the chi-squared value is going to be 28.03, and the p-value for this would be 0.0032. So using this p-value, we would look and say, okay, from this p-value, then we can do compare the p-value with the significance level of 0.05. And again, 0.0032 is less than the significance level, so we reject. Oh no, I keep wanting to spell that wrong. No, I don't know why. Reject is not a hard word. I just keep trying to spell it wrong halfway through. Okay, because our p-value is small enough, we reject the null. Now I did make myself a note about using both methods, so I'm guessing that the homework makes you use another method. So just to make sure you're ready for critical value method, if you were trying to use critical value method, you would look at the 5% significance level and use that to get your critical value. So just a little note, we look at the 5% here for critical value to do critical value method. And then we look at the degrees of freedom of 11. So we go to 11 and look at 5% to the right. And our critical value would be this 19.675, because that's the chi-squared score for degrees of freedom 11 that has 5% to the right. And anything beyond 19.675 would be reject. So the critical value, the chi-squared, would be 19.675. And since we got 28.03, so 28.03 is bigger than that 19.675, because this is a test statistic. This is a critical value. That means, since we're always doing a right-tailed test, we'd be in this rejection region. And so we'd reject the null. So just to make sure, if your homework has you do the critical value method, that's basically what you do. You just take that percentage in your degrees of freedom, and you'd use that to figure out what your critical value is. And that's just your Markov point, because anything beyond that, anything further to the right, we're always doing right-tailed tests with these chi-squared goodness of fit. So anything bigger is going to make you reject. And that's it for the goodness of fit test. We'll see 11.2 of a different test that I believe also uses chi-squareds. But that's it for this section. So I just want you to be ready to do the chi-squared goodness of fit test. Again, if you have a TI-83 calculator that doesn't do it, email me and I'll get you that instructions. But most of us will have this TI-84 Plus, and it has this function, this test built in. So you just got to remember when you do it to get that second list, don't use the percentages they give you. They give you percentages. Those aren't the numbers you use. You always want to find the expected frequencies. So you always take those times the count size. And they don't necessarily tell you the sample size, right? They give you the sample results, but a lot of times you have to add it up to find your sample size yourself. Okay, that is it for 11.1. I'll see you on the next set.